Hi, everybody. So up till now in the course, we have tended to think about one group at a time. And our next tool is a way to compare different groups. And the key term here is isomorphism, which is a kind of a made-up word. Isomorphism means two things which have the same form. And a really fundamental problem in group theory is to try to figure out how many different types of groups there are and to classify them. And if you want to do that, then you need some way to decide if groups which occur in different contexts are actually the same. And for that, the key notion is isomorphism. So let's start with some definitions and examples and then take it from there. So an isomorphism is a function that carries one group to another and that satisfies some basic properties. So here's the formal definition. So we have two groups, G and H. And an isomorphism from G to H is a function from one to the other, which has two properties. So it's bijective. So remember what bijective means. It means that it's injective, or one-to-one, and onto, or surjective. And the reason that bijectivity is significant is because we know that bijective functions have inverses. And so if there's a map from G to H, which is bijective, then there's an inverse map from H to G, which is also bijective. So that's the first property. And the second property that the function has to satisfy is this property having to do with the multiplication in the group. And what this is saying is that if you take two elements in G and you multiply them together and then apply the function f, that's the same thing as if you applied the function f to the two elements G1 and G2 separately. Now you have two elements of H and you multiply them together in H. So this is a product in H. This is a product in G. And so one way to think about this is that the function f, not only does it carry the elements from G to H, but it also carries the multiplication from G to H. And anytime you have two groups G and H for which at least one isomorphism exists between them, you say that those groups are isomorphic. And it can happen that there's more than one isomorphism between two different groups, but as long as there's at least one, you say that they're isomorphic. So let's look at maybe one of the most fundamental examples of an isomorphism, and that's an isomorphism between the additive group of real numbers. That's our group G. And our group H is the multiplicative group of positive real numbers. Both of these are groups, and they seem quite different, but there's a function between them, and the function from R to R star plus is f of x equals e to the x. And if you don't like e, you could take any base a other than 1, like you could pick 2. You could take 2 to the x. And the claim is that this is an isomorphism. And let's think about what that means. So first of all, for it to be an isomorphism, it has to be a bijective map. And one way to check if it's bijective is to see if it has an inverse function. So let's remember the inverse function theorem. Says that f is bijective if and only if it has an inverse. And what is the inverse to the exponential function? Well, it's the natural logarithm. And logarithm carries positive real numbers to all real numbers. And we know that these are inverse to each other because we know that e to the natural log of x is equal to the natural log of e to the x is equal to x, provided that x is in the appropriate domain. So that's the first part of being an inverse, being an isomorphism. But the second part is this crucial property having to do with multiplication. And let's think about what that says. So it's supposed to be the case that f of g1, g2 equals f of g1, f of g2. But we have to interpret that in our particular situation. So on the left, this is a computation in R, in the additive group of the real numbers. And in R, the additive group of the real numbers, we don't write the operation as multiplication, but as addition. And the function is e to the x. So the left-hand side of this equation is e to the x plus y. If I use x to be g1 and y to be g2, just because it looks a little more normal. And what's the right-hand side of the equation? Well, it's f of g1, that's e to the x, times e to the y. And of course, this is true for the exponential function. In fact, this property, e to the x plus y equals e to the x, e to the y, is exactly what you need. So you notice that on the left-hand side, the group operation is addition. And on the right-hand side, the group operation is multiplication, because this takes place in R star plus, and this takes place in R. So the exponential function changes addition in R to multiplication in R star plus. And of course, the inverse isomorphism, which is natural log, which goes from R star plus to R, the isomorphism property there is that the natural log of xy, here we're multiplying two elements together in R star plus, is equal to natural log of x plus natural log of y. This is an addition here in R. So the exponential function and the natural logarithm are inverse isomorphisms to one another between the additive group of the real numbers and the multiplicative group of the positive real numbers. And maybe we'll just notice one other thing, which is what happens to the identity elements? Well, 0 is the identity element in R, and e to the 0 is 1, which is the identity element in R star plus. And similarly, 1 is the identity element in R star plus, and the natural log of 1 is 0 in R. So the isomorphism carries the identity element of one group to the other. And we'll see that that always happens with isomorphisms. We'll see that a bit later. So here's one example, but there's many, many other examples. So one thing which we've kind of beaten around the bush repeatedly in this course without ever having the terminology to express it is that the permutation group on three elements, S3, and the group of symmetries of the equilateral triangle are the same group. And if I label the vertices of the triangle 1, 2, 3, we actually had a map between these. Namely, we send a symmetry where we send a symmetry of the triangle to the corresponding permutation of the vertices. And as we know, there are 6 elements of the symmetry group of the triangle. And so we had the identity element goes to the permutation which doesn't do anything. And if we use cycle notation, it's a little easier to write this down. The rotation right goes to the 3 cycle 1, 2, 3, the rotation left goes to the permutation the cycle 1, 3, 2, and then the 3 reflections correspond to the transpositions 2, 3, 1, 3, and 1, 2. And this is a bijective map between the group of basically, so for instance, the symmetry, the reflection which fixes 1 and reflects the triangle around this axis, corresponds to the transposition that interchanges 2 and 3. So between the sets, this is a bijection. To check that it's an isomorphism, we need to check that this property about composition of symmetries corresponds to multiplication of permutations. And we've actually already done that kind of repeatedly. If we were going to, let's just remind ourselves how that works. So for instance, if I do the rotation right first, and then I do the reflection fixing 1. So what happens there, when we actually do the computation, we practically use the permutations. We say, okay, the rotation right takes 1 to 2, 2 to 3, and 3 to 1. And the reflection around that fixes 1 is interchanges the vertices 2 and 3. And so what's the combined effect? Well, 1 goes to 2 when we first do the first rotation, and then we do the reflection, 2 goes to 3. So 1 goes to 2 and 2 goes to 3, so 1 goes to 3. And then 3 goes to 1. And then this one, and then 2 is left alone. So in terms of the computation, if you want to think about this, this is the reflection fixing 2. So here, under this map F, the reflection fixing 1 goes to this permutation, the reflection fixing 1 goes to this permutation, and the reflection fixing 2 goes to this permutation. So what we've shown is that F of the reflection fixing 1 times F of the rotation right equals F of the product of those two things. Which is this thing, the reflection fixing 2. So one way to express the fact that these two groups are really the same is to say that the permutation group on 3 elements and the symmetries of the equilateral triangle are isomorphic groups. And as we know, for the square, it's not the same. I mean, the square has 4 vertices, but the symmetries of the square are not the same as the permutation group on 4 elements, because the symmetries of the square, that's the dihedral group with 8 elements, whereas the permutation group on all 4 vertices would have 24 elements. And you can't have a bijective map between a set with 8 elements and a set with 24 elements. So this is sort of an accident that happens for triangles. Let's look at another example of isomorphic groups. So remember what U of 7 is. U of 7 are the non-zero things mod 7 with multiplication. And Z6, of course, are the numbers 0, 1, 2, 3, 4, 5 with addition. Now, both of these sets have 6 elements, so there's lots of bijections between them. But if we want an isomorphism, we have to not only worry about the bijectivity, but also about this fact that it preserves the multiplication. So let's notice that if you take the number 3 in U of 7 and you look at its powers, you have 3 to the 1 is 3, 3 to the 2 is 9, mod 7, which is 2, 3 cubed is 6, 3 to the 4th is 18, which is 4 mod 7, 3 to the 5th is 12, which is 5 mod 7, and then finally 3 to the 6th is 15, which is 1 mod 7. In other words, 3 has order 6 mod 7, and the group U of 7 is cyclic, and it's generated by 3. Remember that means that every element arises as a power of 3. And we can use this to construct our isomorphism. Namely, let's send each element here to the power you have to raise 3 to get it. So we're going to send 3 goes to 1, 2 goes to 2. So here I'm taking this number on the left, and this is where it goes. 6 goes to 3, 4 goes to 4, 5 goes to 5, and 1 goes to 6. But these numbers here are supposed to be in Z6, so 6 is really 0. And now this is my bijection. On the left-hand side, I have U of 7, and on the right-hand side, I have Z6. And why is this an isomorphism? Well, because of the same property that we used with exponents. So let's, for example, look at what happens when we multiply 3 times 4. Let's do we'll do f of 6 times 4. This, remember, is in U of 7. Well, 6 is 3 cubed, and 4 is 3 to the 4th. So f of 3 cubed times 3 to the 4th is f of 3 to the 7th. But that's f of 3 to the 6th times 3. And 3 to the 6th is 1. So that's f of 3. And f of 3 is 1. On the other hand, f of 6 is 3, and f of 4 is 4, using this table. And f of 6 plus f of 4, because we use addition as the group operation on this side, is 3 plus 4, which is 7, which is 1. And so you see we've shown that f of 6 times 4 is f of 6 plus f of 4. And so at least for these two values, this has the property that it looks like an isomorphism. Now, we have to check all possibilities. And it's kind of inconvenient to do that in this direction. So to prove these two groups are isomorphic, it's actually a little easier to write down the map in the other direction. So let's define G from Z6 to U of 7 by defining G of a number A to be just 3 to the A. So it's like an exponential function like we saw before. Now, the only thing we have to be a little bit careful of here is that this makes sense, because A here is in Z6, and if you add 6 to A, then in Z6 you get the same answer back. Right? G of A plus 6 had better equal G of A, because A plus 6 and A are the same in Z mod 6. But G of A plus 6 is 3 to the A plus 6, which is 3 to the A times 3 to the 6th. And 3 to the 6th is 1. So the function g doesn't care if you shift your a by 6, and therefore it makes sense as a function on z mod 6. So this is what it means for the function to be well defined. Namely, whatever representative you choose for a congruence class mod 6, when you apply g to it and take 3 to that power, you get the same thing no matter which congruence class you pick. And why is it a homomorphism? Well, it's like an exponential function. G of a plus b is 3 to the a plus b, which is 3 to the a times 3 to the b, which is g of a, g of b. And that's what it means to say that g is an isomorphism. Well, and I guess we should check. I didn't check this. I also have to check that g is bijective. But we actually know that from the table above because we just have to invert this picture here, right? So I just took this picture in the other direction, but we could check it real quickly. G of 1 is 3. G of 2 is 9, which is 2. G of 3 is 6. G of 4 is 4. G of 5 is 5. And G of 6 is 1. So it is, in fact, bijective. It's this thing written in the reverse, and it's a one-to-one and onto math. So these two groups, U of 7 and Z6, are isomorphic. And in fact, they are both cyclic groups with 6 elements. And later on, we'll see that if you have a cyclic group with n elements, it's isomorphic to Z mod n. So in a certain sense, there's only one cyclic group with n elements that can appear in many different settings. Now let's look at a couple of groups that are not isomorphic. Let's look at Z4 and Z2 cross Z2. So Z4 and Z2 cross Z2 both have 4 elements. How do we prove that they are not isomorphic? Well, one way to do that would be to assume that they are. So suppose that F from Z4 to Z2 cross Z2 is an isomorphism. And let's think about the difference between these two groups. So the difference to me is every element in Z2 cross Z2 has order 2. So it has 4 elements. The 4 elements of this group are 0, 0, 1, 0, 0, 1, and 1, 1. And you add them component-wise. So, for instance, 1, 1 plus 1, 1 is 1 plus 1, 1 plus 1. But that's 0, 0 because each component is mod 2. And similarly, every one of these other elements, if you add them to themselves, you get 0 because you're in Z2 cross Z2. So every element of Z2 cross Z2 has order 2. But the element 1 in Z4 has order 4. So let's suppose that F of 1 in Z4 is some element A in Z2 cross Z2. Well, then F of 1 plus 1, which is F of 2, that has to equal F of 1 plus F of 1, which is A plus A. But as we said, every element of Z2 has order 2. So whatever A this is, when you add it to itself, you get 0. In other words, what we've just shown is that if there is an isomorphism, F of 2 has to equal 0. But that's a contradiction, because also we know that F of 0 has to equal 0. Why is that? Well, let's do a calculation. F of 1 plus 0 is equal to f of 1 plus f of 0. This is equal to f of 1, which is a, and this is therefore equal to a plus f of 0. And if a equals a plus f of 0, whatever this is, we could maybe say I'm proving this fact. Since I'm in a group, I can, if I have the equation a equals a plus f of 0, I can cancel the a's and conclude that f of 0 equals 0. So what's wrong here? Well, I've shown that f of 2 is 0 and f of 0 is 0, and therefore my function can't be bijective because 0 and 2 go to the same point. And if it's not bijective, it can't be an isomorphism. So by assuming the group property that f of a plus b is f of a plus f of b, between these two groups, we got a contradiction of the fact that the map was a bijection. And therefore, no isomorphism can exist. And these groups are actually different. And just here's maybe a little bit more interesting one. Let's take the additive group of the rational numbers. And the additive group of the integers. And let's suppose they're isomorphic. So let's suppose that we have a function f which goes from q to, well, let's go from z to q. How about that? My pen is acting up. So suppose this is an isomorphism. And we're going to prove this by contradiction. Well, let's look at f of 1. So remember what that means is that it's bijective. So f of 1 is equal to some number a in the rational numbers. But in the rational numbers, there's a number a, and a is not 0. How do we know a is not 0? Well, if a were 0, then f of 1 plus 1, which is f of 2, also equals f of 1 plus f of 1, which would be 0 plus 0, which would be 0, and so also f of 2 equals 0. And that would contradict the fact that this is bijective because we'd have 2 points that go to the same element. So this shows that if f of 1 equals 0, then f is not bijective. So f of 1 is some non-zero element a. But then we know that a over 2 belongs to the rational numbers q. And because f is bijective, that's an assumption, there must be an x in z so that f of x equals a over 2, because the map is surjective. And if we look at f of x equals a over 2, then it must be the case that f of x plus x equals f of x plus f of x, which is a over 2 plus a over 2, which is a. So this is f of 2x. So we've just shown that f of 2x equals a. Now, we can use the fact that f is bijective to apply the inverse function of f to this equation. And if we apply the inverse of f to that equation, we get the equation 2x equals f inverse of a. But f inverse of a is 1, right? F of 1 is a, so f inverse of a is 1. And this is an equation in Z. In other words, x has to be an element of Z, which solves the equation 2x equals 1. But there is no x. And so we must have a contradiction. So f cannot exist. And again, we have to play off the bijectivity and the group property, because there is a bijection, if you remember from Math 2710, if you covered this. There is actually a bijection between Z and Q. They're both countable sets. I'm not going to explain that now, but that you can't do that and also preserve the operation of addition in the way that you would have to if you have an isomorphism. So that we'll stop there, and then we'll pick up by looking at some theorems about isomorphisms in the next talk.